on this computer. Okay, thank you. All right, so let's me look up question 5. And that, oh, that's the solution. I don't want that one. Question 5. All right, so question 5 says this. An airfield capacitor consists of 2 parallel plates, all right? And I'll draw myself a picture so when I turn on my whiteboard, I can start drawing for you. So an airfield capacitor consists of 2 parallel plates, each with an area of 7.60 square centimeters, like that, separated by a distance of 1.8 millimeters, and a voltage of 20 volts is applied to these. A, the electric field between the plates, or it says calculate, so I'll just put E question mark for A, what's the electric field? B says, oh, the surface charge density, so that's sigma. And then C, the capacitance. Okay, so what is the capacitance? And there's a D, the charge on the plates. All right, awesome. All right, so let me switch back over to my Zoom session here, and let me go to share whiteboard and pick up where we left off. Oh yeah, let's see. We were doing number, and just to help me to confirm, since I don't have my second screen, you guys can see my whiteboard?
Yeah.
Nice. Okay. So I was doing this problem. I forget what number it was. It looked like 29 before the break here. And so let me just scroll my whiteboard up here and angle myself a little bit better so I can write on my screen. And I'll just put here then chapter 26, number 5. And I'll start off by saying, okay, here is, I'll just make 2. What was that little mark there? Get rid of that. 2 parallel plates, and this one is positive, let's just say, and this one is negative, and they give us the separational distance of, no, that's the area, sorry, separational distance of 1.8 millimeters. And maybe over here, I'll just say A, they give us the area of, ooh, better watch your units here, 7.60 square centimeters. And then they ask a whole series of questions. But the one that kind of pops into my head first is C. So I'll do C first. What's the capacitance? Because the parallel plate capacitor was one of the common ones. And we came up with this equation. In fact, this was the equation we tested in the lab. And before the break, you were asking about, I think it was you, Daniel, what do I graph? And that's why we had those 2 factors. One factor was the area, and the other factor down underneath was the distance. And so we changed the distance between the plates in step 6 of the lab and the area in step 7. And we're trying to see if they would match the theory. All right. So with that in mind, that one pops into my head first because they directly gave us the area and the distance. And so let's do that one. Let's get the capacitance. And so equals, and so the permittivity of free space is 8.85 times 10 to the negative 12. Let me be careful with the units here. The units is a Newton and a square meter in the bottom and a coulomb in the top. The area that was up here at the top, the 7.6, but we do want to be careful with our units here, 7.60, and it's centimeter squared. And I'll come back to that, but you can see we really want that in square meters.
Yeah, which is just a simple conversion.
Yeah, so I'll make sure I do that conversion. In fact, I'll do the conversion in the next line with the conversion of the distance, because it's in millimeters, and we want to watch that. So if there's anything hard about this step, it really is, I think. I don't know which is harder. I was going to say converting the units might be the harder, but I don't know, just remembering, and I'll circle it in red, that, you know, this is the equation for a parallel plate, and only for a parallel plate. And I should say an airfield parallel plate. All right, but with that in mind here, now I can do some unit conversion. So there's the 8.85 times 10 to the minus 12 for the number. But here's what I like to do, and I think I've mentioned this a couple of times, is think about this as, I'll put it in red, centimeters squared. And so it's squaring the centa and also squaring the unit meter. So I would write this as 7.60, and the centa would be 10 to the minus 2, and I would square it. And then that would just leave me with the square meters. Now, I forgot to put in my units with the permittivity, so let me do that now. That would be the Coulomb squared, the Newton, and the square meters. But what I wanted you to see is then the square meters would cancel off. And then downstairs, the same idea, treat the milli for what it means, which is 10 to the minus 3, and then over a meter. So then, and maybe I'll do the units first, and the numbers I can just punch into my calculator, but this is kind of nice to see, because if you group, I'll do blue here, the meter with the Newton, that's a joule. And then if you divide it by one of those coulombs, you would be then just left with coulombs per volt. And that's a farad. So sure enough, our units are going to come out to be a farad. And then the number, well, grab my calculator for that. And so putting in the numbers into my calculator, 8.85 times 10 to the minus 12, and then the times 7.6, and then times 10 to the minus 2 squared, then divided by 1.8 times 10 to the minus 3 comes out to be 3.74 times 10 to the negative 12. And so maybe to finish it, I'll write it as picofarads. Okay, so there's the C part of this. Now,
could you do the A part? The A part was
and the electric field?
Yeah, the A part was the most confusing.
Oh, okay. Okay. So it sounds like you already did it, but to get me to A, let me do D and C. I mean D and B. Okay.
Okay.
I don't want to bore you, so I'll go kind of quickly. But it might be good for other people who want to see the video, or even other people might be in the Zoom here with us. But it's going to make, if I do those first, it's going to make A real easy. That's what I'm getting at.
Okay, that makes sense.
All right, so if I do D, because I'll have the definition of capacitance as charge over volts. And they're asking for charge on one plate, so that would be the capacitance times the volt. So we just did and see the capacitance, 3.74 times 10 to the negative 12 farads. And they were given in the problem as 20 volts. So that number, 3.74 times 10 to the minus 12, is still in my calculator. So I'll just go times 20. And that would be 7.47 times 10 to the negative 11. And again, since these units are probably new to most of you, a farad is a coulomb per volt. So that volt and that volt would cancel, and that's how many coulombs I would have. In fact, just to check this at the end, let me write these on a piece of paper, answer C and answer D, so that I can jump over and just see if I did it right at the end. All right, because then I would do B. B would be then sigma, the charge density, and that's just the amount of charge Q over the area. Now again, like we did in the first step, which we did C, watch your units here. I mean, we have the charge, and so it's this 747 times 10 to the negative 11 coulombs. But the area is this 7.60. And remember, that would be centa squared over meters squared. So I'm going to treat that centa as 10 to the minus 2 squared, which is 10 to the minus 4. So in my calculator, I'm going to do this. I'm going to put in the charge, which is already there from the last problem. And then I'm going to divide it by this number, which I'm going to write as 7.6 times 10 to the negative 4. There's the 7.6, and then there's the times 10 to the negative 4. And then I'll hit enter. And so I get 9.83 times 10 to the negative 8 coulombs per square meter. And I will write that so I can check the answer real quick here when I'm done in a second. And then finally getting to your question, so thanks for being patient, is, okay, what is the electric field? And one of the ones we derived back in chapter 24, and I suppose I could redo it if you want here. We talked about it in the last one, if you remember, that very last problem before the break, was we would want the charge density over the permeability of free space. That's the electric field between two charged plates. And so since we just did the charge density in B, 8.83 times 10 to the minus 8 coulombs per square meter. So if I divide that by 8.85 times 10 to the minus 12, and I've always got to rethink about the units for the permeability of free space. We would get, and I'll start with our units because the units are kind of, like I said, new to you. But you can see here that I would have a square meter, cancel out with a square meter. They're in the denominator of, well, the denominator of the numerator as well as the denominator of the denominator. And the one of the coulombs downstairs would cancel off. And so when you flipped this, you would have a Newton on the top and a Coulomb on the bottom. So great, which is the unit for electric field. So that feels good. As far as the numbers go, I have this number, the 9.83 times 10 to the minus 8 already in my calculator from step above. So let me divide that then by 8.85 times 10 to the minus 12. And I again get, it's like 11,011, or it looks like a bunch of ones. And I suppose we could round it to 11,000 kilonewtons per coulomb to see if that, 11,000 kilonewtons per coulomb. And actually, you might already know, did I do it right? Did that agree with?
Yeah, looks like. Yeah, they
No,
got
it's kind of
11.
nice to see too. Sometimes they do something a little different. Like they, one right before the break was interesting. I did it with forces and they did it with energy. And so it was nice to see that. All right, but yeah, they got 11,000, 11.1 thousand. Oh, now, see, this is why I'm glad I looked at it. Did you notice they put volts
Kilovolts over
per
meters.
meter? And for anybody who hasn't caught on with this yet, let me just do this. Let me come back here and write on here. So they have 11.1. Okay, so they did one more significant figure. But if you do this, if you multiply their unit on the top by a meter, of course, then you have to do the bottom by a meter to be consistent. But then this Newton and meter together is a joule. And if you group that with the Coulomb, that would be a joule per Coulomb, which is the unit of a volt. So you could write the electric field as a volt per meter instead of a Newton per Coulomb. And usually when you're writing it as newtons per Coulomb, you're thinking of forces. When you're writing it as volts per meter, you're thinking in terms of energy. But either one is equally as valid. So good. I'm glad I looked at that because that gave me a chance to point that out again. Charge density. Yeah, they got the same number. They did it in nanocoulombs, so I'll go back and change that. Then they did picofarads for C, so that matched. Oh, and then they did pico for the charge also. So I'll just go back and say, okay, when you look at the solution, you'll see that they write this one here as 98.3. So making that bigger made that smaller, made it 10 to the minus 9th, and that's a nano.
Okay.
Yeah, and then they wrote this as a 74.7, so they made it bigger and smaller, so that would be a pico.
If we leave it in a form that's equivalent in a way, like say on the test we did in 11 kilonewtons per coulombs, that would be fine.
Oh, absolutely. Absolutely. Yeah, there's yeah. The only time I would say that wouldn't be okay is if the problem specifically said write it in terms of volts per meter, And I never do that. The textbook does that at times, but I don't. I mean, that's the same thing. So, yeah, and if hopefully I would notice it. Hopefully you would never feel like, hey, this is the same thing and he didn't notice it. I'm usually pretty good at that. I've done this for a long time.
Cool. Thank you.
Cool. All right. Good. All right. So let's go on to Gina's question here. Gina says, Can you do number 40 as well? Thank you. You bet. All right. So, all right. So let me.
The timestamp is 20 minutes, just in case you wanted to make a note.
Oh, good. Yeah, I got one timestamp on the other one here. So
yeah, sorry, I closed the app last time, and I was like, oh, well, whoops.
yeah, I like what you're thinking. I need to. That'll be my goal for next Friday. Hopefully, I'll get better each Friday. And actually have the timestamps on there. Okay, so number 26, number 40. Okay, a timestamp 20 minutes, and then let me switch back my screen so I can actually find question 40. That must be a little further down here. 40. So 40 says a parallel plate capacitor in air has a separation of 1.5. I better start making myself a picture here. All right, so a parallel plate, so two lines. Parallel plate capacitor in air has a separation of 1.5 centimeters and a plate area of 25.0 centimeters squared. Good. The plate is charged to a potential difference of 250 volts. Oh, and it is now disconnected. Ooh, okay, this is going to get good. The capacitor then is immersed into distilled water. Determine this is a very important question here. The charge on the plate before and after it is immersed. So Q, before and after, right? And then B, the capacitance and potential difference. So capacitance and potential difference, there's two in there. After, so good, I better put after. And then C, the charge in energy of the capacitor, assume that the liquid is an insulator. It doesn't look like that. Copied real well. All right, but they put it in distilled water. And that's going to be important here. But let me start with the beginning. And now that I have the question, let me come back to my whiteboard. And am I still sharing? Let's see.
Not at the moment.
No. Okay. So I turned that off. Or okay. Boom. Okay. Yeah. I must have turned it off. I need to turn it off to get back to see the chat, I think. But anyways, all right. So here's the one we just did. Let's move this one out of the way. Okay. All right. So I'll write here. Oops. You guys can't see, but I actually picked up the real pen and started writing on the screen. That's not good. All right. So let's go to chapter 26, number 40, for anybody who's kind of scanning the video quickly. And this first part, of course, is a lot like the other capacitor. I'll kind of draw it here. Here's the parallel plate capacitor, and what they said is the separation is 1.5 centimeters. The area is 25 centimeters squared. It doesn't matter really what side we charge, positive versus negative. They're just metal plates. Although, I should point out that's kind of the basic thing, but with today's fancier capacitors, you guys should begin to learn, and you'd probably do this in a real circuits class. So those of you who are going on into some major that needs you to take our circuits class, and some of you are in there, would be sometimes the material they put in between is special material that it does matter, and so they'll mark those. But for us, just trying to learn our basic science, we'll say, look, it doesn't really matter. They're just two plates, and let's just say they're aluminum plates, and so making one positive versus the other one doesn't really matter. So I just pick one direction over the other here. All right. But they gave us not only the what I'll call the geometric factors, the area and the separation between them, but they said they've hooked it up to a pretty good power supply that can supply 250 volts. And in A, they ask for the charge, and they say both before and after. So let's start with the before. Because as they're looking for charge, I'll just start off here and say, remember, the definition of capacitance is the charge over the voltage. So I just need to find the capacitance. They gave me the voltage and I can get the charge. So I'll write it this way. Charge is capacitance times the voltage. And then I'll just go off to the side here and remember that they said it was a parallel plate capacitor. And we've done a few of those, and most of our problems will be parallel plate capacitors. They're really easy to build and to work with. And so this would be 8.85 times 10 to the minus 12. And again, just as a reminder, the units here have the Newton downstairs, the meter squared is also downstairs, but the Coulomb squared is up here. But it's that square meter that I want to come back here because, again, looking at the area of the plate, let me write that, as I did last time with some red 2's in there. Cross that out. So it's the centa squared as well as the meters squared. So I could write that as 25 times 10. And a centa means 10 to the minus 2. So if I square it, I get 10 to the minus 4 square meters. So coming back then over to here and putting the area, I'm going to write it as 25 times 10 to the negative 4 square meters. And then likewise for distance, right, centa here means 10 to the minus 2. So this down here would be 1.5 times 10 to the minus 2 meters. And so for my capacitance, and I'll do these units a little faster now that you guys have seen them a couple of times. These square meters would cancel off. This Newton, I'll do it in red again. This Newton combined with that meter would be a joule. Taking one of the coulombs and putting it underneath would be a volt. So this would be then a joule, or excuse me, a coulomb per volt, which is a farad. So this is going to come out in units of farads. So like I said, it's probably worth going through that a few times yourself to get yourself familiar with some of these new units, especially the farad, probably new. Voltage is probably still fairly new, and although you probably heard the word before. And coulombs, maybe the same thing. Meters and centimeters, I know you're familiar with. But now if I grab my calculator here, and so in the numerator, 8.85 times 10 to the negative 12. And then the area, 25 times 10 to the negative 4. And then divide by 1.5 times 10 to the negative 2. I get a 1.4 that's rounded up to 8. Times 10 to the negative 12 farads. I suppose we could even write that as 1.48 pico farads. So that's the capacitance, and that's before we submerge it into this distilled water. So I don't think that was the answer to any of our questions. But we needed that for this first step A. So I'm going to bring this back over to here and then put 1.48 times 10 to the minus 12 farads for the capacitance. And the voltage, if I remember, I wrote 250 volts. Yeah, there it is. Okay, so let me come back up here. 250 volts. And again, in terms of units, remember that a farad is a coulomb per volt. So when you multiply it by this volt here, it will cancel with that volt, leaving you with coulombs. So grabbing my calculator, I already have this number for the capacitance in there. So I'll just go times 250, and I get 3.6, and I'll round it to a 9 times 10 to the minus 10. Now, based on the last problem we did, it wouldn't surprise me if they then increased this number by a factor of 100, decreased that one by a factor of 100. So that would become 10 to the minus 12, which then is a pico. So when I get done working on this, I'll check that answer. But 369 picocoulombs, I think, is what they're going to list here before. And I think it was Gina, right, who asked this. And I'm going to guess here, Gina, that wasn't so much of your problem. Could have been. That was kind of the beginning stuff of this chapter. Here's where the problem gets hard then is, what about after? And this one, and I say this one because this is not always the case, but in this one, it made it sound like they disconnected it from all the wires. But you know what? I'm going to go back and just read it again. Parallel plate capacitor in air has a separation of 1.5 centimeters and a plate area. The plates, that must be R. The plates are charged to a potential difference of 250 volts, and there it is, disconnected from its source. The reason I want to emphasize that is here's what they wanted you to figure out from that. I'm gonna put another picture of a capacitor. It would look like this. There would be wires coming off. You would connect it to some kind of power supply, just for the lack of picture here. I'll say, let's say this was a battery. Maybe I'll make this the minus side and this the plus side of the battery. So the little knob would be back here. And so the wire would go like this and go like this. And so this would become positive and this would become negative. But here's the key to the problem, and I'll use my eraser. If you disconnect it right there and disconnect it right there, the charge is stuck on that plate, and the charge here is stuck on that plate. So if you go ahead and you submerge it into water, and assuming the water, and that's why they use distilled water, is a pure insulator, there's nowhere for this charge to go. And conservation of charge, going all the way back to chapter 23, conservation of charge would say, hey, it can't go anywhere. And because of that, then I'm going to come back up here to this charge and just say that afterwards, we still have 369 picocoulombs. 300. Yes. Look at my pen. It seemed like it was writing kind of light, so I wanted to go one darker. So that is probably the big step. Again, I don't know if that was your question, Gina, here, but that's usually a lot of questions that students have. And I want to emphasize, they could have given a different type of problem, and I think they do later on. They could have left it hooked to the battery. And in that case, then the voltage would remain constant, but not the charge, because the charges could still flow on and off, but the voltage is determined by the chemical reaction inside of the battery. And so circle that in green. And so that's a little different for, like I said, a little different reason here.
Dr. Young, it says before and after immersion in water.
Right. Okay, so let me say it again. So I'll come back here. So before. So let me kind of underline up here, before. Okay. So before you put it in the water, before you immersed it, you had this charge, 369. And then what I'm trying to say in here is that charge will not change. The way they described it, this is the key, by disconnecting it. Disconnecting it means you cannot put more charge on, nor can charge come off. That's the principle of conservation of charge. And so therefore, even after we submerge it, we still have 369. We don't have more, we don't have less, it doesn't change. Conservation of charge. Did that help?
I think I follow you. So it's not before and after disconnection?
Well, it is before and after, but what they want you, how can I say this in clear in words? The answer is the same before and after. It didn't change. And that's really the point of the problem, is to recognize that it doesn't change. The charge doesn't change. Now, there's still some hard stuff in B, but I think the hard stuff in A is to recognize, because of conservation of charge, it does not change. So maybe I should move on to B and let that kind of soak in for a little bit.
Yeah, that sounds good.
Okay. So, and I'll say it one more time. Maybe think of, I got an idea. Maybe think of these as a bunch of tennis balls that are in a basket, because you got them all in this basket before you put them underwater. And if you have 369 of them in the basket before you put it underwater, and then you shoved it underwater, well, how many do you have now? Well, you still have 369 if you don't open the basket and let some of them out. Now, if you do open the basket, then they can float out, because tennis balls float, and you might have a different number. But if you have a closed basket with no way for tennis balls to get in and out, the number of tennis balls will not change. And so this charge is coming from the number of electrons. They will not change. Okay. Now, other things change, and that's where B comes into play. And so B is a little bit harder. And so B is saying this: what's the capacitance? That's kind of the first charge, or the first part of the question on B. And this is where the dielectric constant comes into play. This is exactly what, I believe it was step 8 in the lab this week. Could have been 7. No, 7 was where we changed the area. So it's a step 8. Step 8 in the lab of this week was to show you that if you put some material between the plates, and my little kappa doesn't look very good. Let's see if I can make it a little better. That's still not a very good kappa. But I hope I'm getting across to you that this is that dielectric constant. This is the material that's between the plates. So the capacitance goes up depending on what you put. In fact, based on a conversation I had in the last session, the first piece of plastic that we put in there, which I think was really vinyl, The student said that, because I didn't run the numbers, but they said when I measured the capacitance before and after, it went up by a factor of 3.6, which would make a lot of sense because if you look on that chart in the chapter, it goes up. It says vinyl is like 3.4, and so we're right on about pace for a piece of vinyl. And I wasn't really sure, and I'm still not really sure what kind of plastic we were using, but but I'm pretty sure it's a vinyl. And I'm sorry, no, nylon. Oh, see, I'm confusing myself. I don't know, but I know that it was about a 3.6 is what it went up by. So that's what we need to do now. In other words, we know that this capacitance, let me go back to A here, which we calculated earlier as 146 picofarads. So this number is let's say 100, no, only 1 point. Did we really get a number that small? Let me look back at my calculator. Yeah, that's what I got. Okay. 1.48 picofarads. That's small. Okay. 1.48 picofarads. And so that's what we got when it was filled with air. And so this one is now going to be filled up with water. Presumably, when you submerge it, the water, leaks between the plates and gets all over. And so I need to look this number up, and that's what that chart is. And I'll switch my screen here, and let's see. Go back to my Zoom here with you. I'll stop that one for a moment. But I think I set up the textbook earlier today for just that reason. I think here's the textbook, and share that. Yeah, so here is the start of chapter 26. Let me just go through the pages because they first just talk about capacitors in general and free space without any material in there. So I think we're going to have to go a little bit. Here we go. This is it. Here's table 1. And I'll make it a little bigger here and then scroll down to the table and then figure out, whoops, looks like I went too far. What is the dielectric strength of I'm getting myself sidetracked here. Nylon says 1.4. So our plastic was either nylon, but it could have been PVC, which is also 3.4. And yeah. So who knows what, I'm still not sure which kind of plastic we're using in the lab. But anyways, let's get to water. Do I see water on here? Here we go, water. Pure water is a factor of 80. And so keeping that in mind, I'll stop sharing that and then go back to my whiteboard and know that, okay, so what I need to do is put in factor of 80. So the capacitance is going to go up by 80 times. So 80 times 1.48 comes out to be 118.4 picofarads for the capacitance now that it's underwater. So that's the one they wanted for B. What is it afterwards? And the other part of B is this, that remember, capacitance is the charge over the voltage. And I'm going to circle this in red. This is worth pausing for a moment because this can often throw the beginning student off a little bit. Notice that if you change one of those parameters, at least one other one has to also change. And if you remember, and I'll circle it in blue, I said that the way they had ours, the charge is not changing. So we just changed the capacitance by a factor of 80. So that means the voltage must change by a factor of, and I think it would be 1 over 80. Isn't that true? Let's see if we can rewrite this. So here's the charge, which equals to capacitance times the voltage. And we could either recalculate it or just do factors of 80. Maybe I'll just recalculate it. That might be less confusing. But maybe drawing in blue, if we said this capacitance just went up by a factor of 80, then this voltage must go down by a factor of 80 in order to keep the Q the same amount. So we had started at a voltage of 250 volts. So if we reduce that by 80, and I'll do it the long way here in a second, but I'm kind of curious. This is what I'm expecting. 250 divided by 80 is reducing it down to 3.125 volts. And so my calculation, I guess I would do this way. If I said, well, what's the voltage? I would take the charge and divide it by its capacitance. And this would be after you submerged it in water. So after you submerged it in water, as we said, the charge would be this 369 picocoulombs. So 369 picocoulombs. And I'll say it again back in A, that's the same number before and after. So it can get confusing, but I'm actually using the number after because I want to know the voltage after, so I need to use the charge after and the capacitance after. And the capacitance after is what we just did here, 118.4 picofarads. And the 10 to the minus 12 shows up on top and bottom, so that'll save me a little bit of math. I won't actually need to do that math. And so I'll just take the 369 and divide it by the 118.4 and come up with a 3.12 volts. Yay, and so sure enough, that does match that. Although, like I said, just divided by 80 would have been a lot easier and a lot faster, but nice. And since I did a lot, I should probably just double check what I get for voltage, 3.12. I don't know if anybody looked at the answer to 40 and see if I'm on track, but I will. Scroll down, here's 40, and there they go. They say the charge, and then they say, yeah, so in A, they say the charge before and after it would be the same, and that would be 369. And then B, they say afterwards you would have a capacitance that increased by a factor of 80, and they get 118 picofarad, and then a voltage that would decrease by a factor of 80, which would be 3.12. Nice. Okay, good. All right, so I'll stop sharing all that for a moment, and hopefully that helped, Gina. Okay, so was Gina. All right, quick question. Elizabeth. I think I lost Elizabeth here. I don't see her.
Oh, isn't there one more part to that problem?
Oh. Okay, let me go back. I don't remember one more part, but was there a part C I overlooked? Oh yeah. Part C. Part C. The change in energy of the capacitor. Yes. So let me write that down because they're looking for the change in energy. And sorry about that. All right. So let me go back to my whiteboard here. No, let me go to the Zoom to share my whiteboard. Okay, so let me go to the Zoom, screen share whiteboard. Let's keep working on this one. Okay, so there is a part C. And we've got a couple of equations, 3 of them actually, for calculating the energy. And I think we could use either one of them. The one that I guess is kind of sticking in my head right now because the charge doesn't change is this one here, I'll write it. That is the energy is Q squared over 2 times the capacitance. And so you can see that the capacitance changes, but not the charge. So there is going to be this change in energy. And so if I go U, maybe I'll put a delta U. And so maybe I'll go F for final and I for initial. This would be a Q squared, and I'll just put a final, but that doesn't really change, over 2 and C final, minus Q squared initial over 2 initial. And the Q's are the same, and the 2 is the same. So if you'll let me just factor out a Q squared and not call it final or initial, just leave it as it is, then this would be the final capacitance, and this would be the initial. All right, so the charge was the 369 times 10 to the minus 12 for picocoulombs. And I'll square that. Then there's the 2. And over here, there's the 1 over. And the final capacitance, I need to come back up here to say, what did we get for the final capacitance? Yeah, this is where the initial was increased by a factor of 80. And it came out to be 118.4. So I'll come back here and put 118.4 picofarads. And then before, or what I'll call the initial, that was that 1 point, and I'm drawing a blank. Was it 4848 picofarads? Let me scroll back up. I think that's what was here. Yeah, there it is. I'll circle it in red. So there was before and there was after. Okay. Okay, so then equals, and I'm trying to think of the best way to do this on my calculator. Maybe it's just put the numbers in. Yeah. All right. So I'll start with this parentheses thing here and subtract that one, because this is 118.4 times 10 to the minus 12, and then I'll take the reciprocal of that. So I'll hit the reciprocal key, then minus 1.48 times 10 to the negative 12, and take the reciprocal of that, and hit enter. Once I have that, I can then go times, by the way, that comes out to be a negative 6.67 times 10 to the 11. So then times 369 times 10 to the negative 12, and I'll square that, and then divide all of that by a 2. And so I get a decrease of, oops, let me get rid of the red, a decrease minus 4.54 times 10 to the negative 8. Oh, and I probably should run through my units, but that would be a joule. And if I switch over, I'll leave the screen on here and go to the solutions. How come and I apologize, I do see now there is a part C, and they came up with, oh, wait a minute. Well, they got a negative 45.5 nano. Let me come over here. Oh, yeah. Okay, so we're talking about the same thing here. So negative 45.4. And since that gets bigger, that's got to get smaller. 10 to the minus 9 is a nano. So nanojoules. So, yay, we get the same crazy number.
I used the 1/2 CV squared formula.
I didn't use that. Would you like me to use that one too?
Oh no, I meant to say that the author used it.
Oh, yeah. Okay, so yeah, the author, besides the units of the nano, yeah, the author used the 1/2 CV squared, which is fine. I did not use that one because that equation, the C changed and the V changed, but it doesn't really matter. I just knew if I used the one with the Q in it, I could factor it out because it wouldn't change. So I liked it in my head.
All right. Hey,
Yeah, in fact,
thanks for going over it.
yeah, in fact, I'll point out up here that you could have just as easily, back up here, said 1/2, and you could say C final, which we know, and V final, which we know, then minus 1/2 C initial, which we know, and V initial, which we know. And you'd get the same number. And that's what your author did. So good. All right. So if that helped you, Gina, I'll go on here. Oh, quick question. Oh, so the 102 has a quick question. I don't know. Oh, good.
I think I answered it in the comments.
Oh, okay. Is this, I want to read it though here because I think I like this one. It says, yeah, that in chapter 1, exercise 2, why did you use 365? Was it rounding? And then, yeah, because the average is 300, yeah, with the leap year or with the leap day is 365. Yeah, and then Elizabeth says, oh, I got it. Thanks for everything. Yeah. Okay, good. Thank you. And then you write converting from value of more than 4 years, vice versa, more likely, yes. Sometimes the book can be inconsistent. Yeah, the book can be inconsistent and drive you crazy when you're trying to learn sometimes, going, why do they do a quarter? In fact, if you want to know a fun, better number, forgive me, I just can't resist here. I'll come back to share. But here's a more accurate number. It's 365.2422. And the best way to think about this number right here is 25 or 0.25 minus 0.01 plus 0.0022. Because it's this plus that most people know means a quarter. You add a February 29th once every 4 years, and this year was one of those. But what a lot of people don't recognize is we do not add a February 29th every 100 years. So on the century mark, like 1900, there was no February 29th. In 1800, there was no February 29th. In 1700, there was no February 29th. I deliberately did not put 1600 or 2000 because, yes, there was a February 29th and a February 29th. And the answer to that is back here, this number right here. You can think of 0.0022 as being 0.0025 minus 0.0003. And that number, oops, I meant to put plus. That number is 1/400. And so what we do with our crazy calendar is right here, we put in a extra day, February 29th, one every 4 years. But every 100 years, we take it away. But then we add it back every 400 years. So the year 2000 is kind of a very special year because the last time we had a February 29th on a century mark because of this 1 in 400 was back in 1600. But yeah, well, anyways, like I said, couldn't resist. But yeah, if you found that interesting, great. Otherwise, I better move on here. All right. So let's go on to where Elizabeth. So Elizabeth says, thank you. Good. And okay, good. And then number 10. Alicia, right? Alicia,
yeah.
Yeah.
And the
Okay.
timestamp is going to probably be 1 hour, 5 minutes.
All right, thank you. 1 hour, 5 minutes. I will put here, what number is this? Chapter 26, number 10. Nice. And now that I bored you guys, leap year question, I'll just throw that in between there. Okay. Oh, hey, what was the last one we did? Did I write that one down? Was that number 40?
Yeah, it was.
Okay, good. So I did write that one down. Okay, so give me for a second here. I'm going to jump over to the question first, and I'll read it and maybe write a few things down about it. But chapter 26, number 10, I guess I got to scroll up for that. Here it says that we have a 10 microfarad capacitor has plates with a vacuum between them. Each plate carries a charge of magnitude. So Q equals, looks like 1,000 microcoulombs. So that'd be 1 millicoulombs. Okay. And oh, then maybe I better put here, it says it's a 10 microfarad capacitor. And at least at the moment, it's a vacuum. So that's, permittivity of free space, no dielectric constant. A particle with a charge of -3 microcoulombs and a mass of 2 times 10 to the negative, that is 16 kilograms. Oh, it's fired from the positive plate towards the negative plate. Okay, so let me think about this for a second. So one plate's positive, I'll mark that one as negative. It is shot from the positive towards the negative. And it is a—
You're not sharing your screen. I didn't know if you think you were.
Yeah, no, would you like me to share it? I thought I just—
No, that's fine. If you're writing stuff, that's cool, yeah.
Yeah, I thought I'd just read it to you guys, and you already knew it, but for me to catch up to you. Okay, so okay, so it's fired from the positive towards the negative plate with an initial speed of 2 times 10 to the 6th meters per second. Does the particle reach the negative plate? Explain how you can tell. If it does, what is its impact speed? If it does not, what fraction of the way does it get? Okay, great. Now, I will tell you that kind of the hint for me here is, I was trying to click on the share button and I messed up. But the hint for me, and I think this, if I share this with you, you may recognize that it's really asking how far did it go. It's a distance question based on speed. And so all of those trigger in my head an energy calculation. Okay. And so so did I share my screen okay here? You got, and I'll put here.
Yeah, I can see it.
Yeah. Okay, good. So chapter 26, number 10. And all that description looked something like this. I'll give a little bit of space. Let's say this is the positive plate here. And of course, that would make the negative plate over here. And this little object is being shot over like this. And because it has a charge of -3 microcoulombs, it's being repelled and it's being slowed down. And so it's a little bit like in physics 121, where we would throw something up into the air. And as we would throw it up in the air, the force is pulling it down and it's slowing it down. And so you could very easily do this with forces and acceleration. But because they were asking about distance traveled and speed, my mind is thinking energy. Okay, so with that in mind, the first part of it, does it make it all the way? All right, so I'll try that first. Because I know that the change in potential would be the, or potential energy, would be the charge times the change in the potential. And so I want to, I guess, first do kind of a side calculation and say, okay, well, what is the change in potential on this capacitor from one plate over to another? Because then I will use that down here and see how much energy would be required to go all the way across. So this is the charge over the capacitance. And so they said that the charge on the plate is 1,000. And then they said micro. I'll just maybe just write it as microcoulombs for now. And over a capacitance of 10 microfarads. And here they gave me some easy numbers. Micro would cancel with micro. Remember, a farad is a coulombs per volt. So I would just put a volt there. And so this is 1,000 divided by 10. That is 100. All right, so I guess I won't even need a calculator for that, but there's 100 volts between one plate or another. And so to get then this -3 microcoulombs of charge, to make it across the whole thing, which would be 100 volts. And I suppose I should also be careful here with my sign. I'll put a negative. I know back here, circle it in red, I calculated a positive. But remember, when we're dealing with capacitance, we don't usually write it, and we probably should be more careful. This is the absolute value. This is the change in the voltage of 100 from one plate to another. And we just like to use the number. We don't like to specify, because we already know, or at least in theory know, that the positive side, so over here, has got to be at a higher voltage than the negative side, a lower voltage. And so we like to just say that the voltage between the two plates is 100. And if you went from negative to positive, it would be an increase of 100. And if you went from positive to negative, you would decrease by 100. And so that's really what we have, is we're going from the positive plate to the negative plate. So that's why I'm putting in here a -100. It also helps too, because you can begin to see now the negative charge with the negative change in potential. Two negatives make a positive. So this is a positive 300. And there's the micro. And of course, remember that a volt is a joule per coulomb. So if you write that as joule per coulomb, the coulomb would cancel and it would be joules. So the first part of this question, which I'm still trying to answer, will it make it all the way across? I know this. It needs 300 microjoules of energy in order to do that. And so again, it would be like throwing an object up in the air and asking it, is it going to make it to the top of the cliff? And the cliff is 100 feet tall. Well, you can calculate how much potential energy it must have there, because it must get it from its kinetic energy. So let's do that. Let's calculate what is its initial kinetic energy. Your initial kinetic energy is 1/2 mv squared. And I should put initial. And let's just see how much kinetic energy it has. Does it have enough kinetic energy? And so again, just like tossing an object in the air, as soon as it leaves your hand, you would say, okay, how much kinetic energy do I have? Because it can never go up to a point where it, you know, had more potential energy than the energy it started with. That's the principle of conservation of energy. So knowing that, I'll put in the 1/2. The mass of this thing was 2 times 10 to the negative 16 kilograms. Okay. Its initial speed was 2 times 10 to the 6th meters per second. And so I'll square that. And so grabbing my calculator, I've got a 1/2 times a 2 times 10 to the negative 16, and then a 2 times 10 to the 6 squared, and hit enter. And this comes out to be 400 microjoules. Well, 400 microjoules is more than the 300 microjoules it takes to get across. So yeah, this would get across, definitely. It would use up 300 of its energy to get there, and then it would have 100 left over, but it definitely has enough energy to get there. So the first part of this question, which was the big one, is does it actually get there? Yes. Now, let me just leave this screen and come back, because I think it said, okay, if it does get there, then how fast is it going? I believe it said. Does the particle reach the plate? So yes. Explain how you can tell. And so I did it in terms of energy, not forces. That would have been another way. If it does, what is its impact speed? Okay, so that's where I am. If it does, what is its impact speed? So I guess I'm looking at something like this. Conservation of energy says, okay, your initial energy is equal to your final energy. So in this case, I would say my initial kinetic and my initial potential must equal to my final kinetic and my final potential energy. So I describe it like this, that I am starting with 400 microjoules of kinetic energy when we are at the positive plate. And so that'll be my reference. And so again, just like in 121, we got to call someplace 0, and we can pick anywhere we want. So I'll pick the plate. Okay, so the plate is 0, the positive plate, because this one is kind of asking what's the final kinetic energy. And what we calculated earlier is that there would be an increase of 300. Let me just double check that number. Yeah, see, there it is, 300 microjoules as we move to the other plate. And maybe this didn't need me to do a whole calculation for it, but here is what I'm looking for, is that then there would be 100 microjoules of kinetic energy when it got to that plate. In other words, it lost a little bit. And if going with my analogy, this would be like throwing an object up very, very fast and asking it, did it get to the top of a 100-foot cliff? And when you calculate it, you calculate, yeah, this thing has more than enough energy to get to 100 feet. It would go way beyond it. Okay, but at the 100-foot mark, you have to take away that amount of energy it took to get there. And so you still have some kinetic energy, so it's still going up. And so that's where I am. And so I would still have this 100. And so if I write this as then something like this is where I would then get the final speed. And so the mass would be this 2 times 10 to the minus 16 kilograms. And the final velocity is what we're after. So on this side, I'm going to write it as 100, and I will write this as 10 to the minus 6 joules. Because I knew a joule has a kilogram in it, and that would cancel off. And then when I take the square root, it's going to give me just meters squared. And so my units are going to come out to be meters per second. So grabbing a calculator, I'll go 100 times 10 to the negative 6. And then multiply that by 2 as I bring it over, and divide that by 2 times 10 to the negative 16. And then take the square roots of all of that. And I get a speed of 1 times 10 to the negative 6 meters per second. Oh, not a negative, well, positive 6. 1 times, so it's a million meters per second. So it started at 2 billion meters per second and slowed down to 1 million meters a second. So it's still going really fast. And out of my own curiosity, jump over to solutions here and just kind of double check before I leave that and say, did I do anything? Oh, good. It says it will reach the negative plate and it will be traveling at 1 million meters per second. I'm kind of curious, did they use energy or forces? And they did it with energy. Yeah. And again, kind of what goes off in my mind first is to do this one with energy. Nice. All right, so stop. All right, did that help? All right, next one. From 121. Oh, great. We had a quiz on Wednesday. Is it possible to do one of the problems? Oh, absolutely. I'd love to. I haven't had any 121 today. I don't know. Actually got me a little concerned that maybe I wasn't very helpful to 121 people, or maybe it's because you took a quiz. That'd be more positive than to say I wasn't very helpful last week. So the quiz is on Canvas. Can I share my screen? And I don't have a microphone. Good. Well, okay. Yes, you can share your screen. Let's see. I believe I need to allow you to first, though. Yeah, okay. So share your screen. Got it. As long as I'm not sharing, and I am not sharing, right? Am I still sharing? Share. Oh, good. Good. Hang on here, I messed. Okay, so thank you. All right, let me read your problem. Lucky throws a ball straight up with a speed of 12 meters per second at time 0. At time 1 second, Kamel throws a ball. Oh, okay, so this is another person. Okay, throws a ball straight up and from the same spot as Lucky. Okay, that's good to know. With a speed, let me change my picture here. Okay, so 1 second later, Carmel throws it at 15 meters per second. This over here is Lucky, okay. For this problem, assume, number 1, no air resistance. Okay, number 2, acceleration is 9.8, yeah. At some later time, the two balls collide. Calculate the height above the point where they are thrown, where the collision occurs. Hint, write an equation for the position as a function of time for Lucky. Okay, good. And another equation for Carmel. Hey, oh, yeah, this. Okay, and let me say, here, you probably already experienced this, but I think any problem that involves two objects, and especially if they have different accelerations. Now, this problem doesn't have different accelerations. They each have only one acceleration, so that's good. But any problem that involves two objects, and in this case, two objects that leave at different moments in time are challenging. So I think I've got yours. I'm going to unshare the screen here. Okay, well, okay, you did that already for me. Good. I'm going to go over to the whiteboard and start talking. And I'll just talk, and if you have a question or whatever, shoot it off in the chat, or if anybody else is watching up, tell me there's a question there, and I'll jump back. But I want to make sure I get all your question here. I'll just make a big line here, and and I'm going to put on my little notes a 121 question. Maybe get that a little more structure when you guys get the video of this. All right.
Do you want the timestamp from a couple minutes ago, or starting right now?
I didn't want to bother you.
No, no worries. So, I mean, a couple minutes ago when you started, it was like 1 hour, 23 minutes. But if you want to say starting right now, it's like 1 hour, 25 minutes. I don't know.
Yeah. What should I do? I'll go 25. Yeah.
Okay.
That'd probably be a little cleaner than me learning the problem. Okay. So let's do this. Let me move this stuff up all the way off of my screen, and I think it'll be off of your screen. Okay. So let me go over here and kind of represent Lucky. Now I know they're at the same place, but for just a moment, I'm going to just draw them separately so I can kind of write out an equation. And really kind of the hints that I like to give students in 121 is make yourself a little chart here representing one object. And so this is the object thrown by Lucky and Kamel. I'm not real sure. Now, I can't remember if they said what object it was, or if it was a baseball or whatever, but I think they just said object. And so let's start off by putting the equation x equals to x naught plus the initial velocity times time plus 1/2 acceleration time squared. Okay. And I would do something like this, and this was kind of the hint, write the equation for the position of the object thrown by the first person, Lucky. And so let's say it leaves Lucky's hand, we'll call that position 0, leaves with a velocity of 12 in the upward direction. That upward direction is important. It's a plus. And the acceleration is down, so I'm going to put a negative 9.8 and then put a t squared. And so this equation becomes 12t minus 4.9 t squared. All right, now for the second person, same kind of logic. Maybe I'll just write out the equation in general first. And I'm going to do the same thing. But here's where a little word of caution is. Well, not here. This is 0. Okay. And also not here. This is 15. But it's this step right here that I'm about to do. The time that this object has been flying in the air is 1 second less than the time for Lucky. So if I use t in my equation, as I did back here, and I don't know if this was a hard part for you, but in general, when I've worked with students in the past, this is where they get themselves into trouble, is keeping track of the time. And when I first did Lucky, t was the time since it was released from Lucky's hand. So if you continue to let t represent the time when it left Lucky's hand, what you need in this whole equation is t minus 1. The time the object has been moving is 1 second less for Carmel's object than for Lucky's object. And so now these T's are the same. The T in my first column with Lucky and the T in the second column for Carmel is exactly the same T. All right, now, of course, continuing on, I would then have a 1/2 9.8, oh, excuse me, negative. Let me erase that there. Put in the negative 9.8. And then it would again be a T minus 1 squared. Okay. And we are trying to find then when they are at the same position. So I guess I would start by trying to get the time when they're same position. So if I take the 12t minus 4.9t squared, that would be the equation for the position of Lucky's object. And I set it equal to the equation Carmel's object. That's when I would set those two equal. And then I've got a reasonable amount of algebra to do here. I will use the 12t and the 4.9t squared alone. This will then be a 15t minus a 15 when I do the distributive. And this, I'll do 4.9. And if you remember, your a minus b squared is a squared minus 2ab plus b squared. And so if you let me do one more line, this is 15t minus 15. This would be minus 4.9t squared. This would then be a plus 9.8t. And then this would be a minus 4.9 as I do the distributed property on that one. Okay, so let's see what I have. And luckily, I thought this math was going to be a little bit harder. Good, I just see it now. I'll circle it in red, but the negative 4.9 t squared on that side and that side cancel off. Nice. Anything else? No, but if we go to maybe solve this a little bit, maybe I'll do this. Go back to black. That 12t and that 15t, when I bring it over, makes 3t. And then I have plus 9.8t. So I think I took care of that one, and that one, and that one. The other ones I need to take care of is this 15 and this 4.9. So I'd make 19.9 and 19.9. It becomes positive when I move it to that side of the equation. So I think I've got all those. In fact, I could simplify this. If I add 3, what's that, 12.8? So 12.8t. And so t would be this 19.9 over 12.8. Oops. So t. So grabbing my calculator, it looks like 19.9 divided by 12.8. And that would be a time of about 1.55 seconds. Now, I don't think we're done, because if I remember reading your problem right, it said the position of when they meet. Now, I suppose what I feel really good about is that it's more than 1 second, because I know it's got to be more than 1 second, because again, the second object isn't even thrown till 1 second later, and we're measuring time from when the first person, which is Lucky, threw it. So I'll go ahead and jump back to maybe the equation for Lucky and put in that time. And so taking this equation right here, didn't want to do that. Now that I messed up the equation. Where's my undo? There we go. I'll just rewrite it. I was thinking I could copy and paste it, but I'm not that proficient at the whiteboard here. So then the position of Lucky's object should be 12 times that number, 1.55, minus 4.9, 1.55 squared. Let me just double check. Is that what I had there? Yeah. So grabbing my calculator, it's 12 times 1.55 minus 4.9 times 1.55 squared. And I get a position of 6.83 meters. Okay. And I'm a little curious, just to kind of check, especially if this was as important as a quiz, although time might be of the essence also. But let me put that over here into the second person, Carmel's equation, because this would be 15 times, and then it'd be 1.55 minus 1, so it'd be 0.55. And then minus, and then 1/2 of 9.8 here would be 4.9. And then times 0.55 squared again. And let's see if I get the same number. And I got an error. What did I, oh, I inputted it wrong here. Okay, let's, all right, see if that is better. Okay, so 15 times 0.55 minus 4.9 times 0.5 squared. All right, enter. And I get, well, within some rounding, I get the same number, 6.76. So I think I got that. Did I miss anything? I'm going to stop sharing and come back to you if you ask me a question in the chat. The position I got was 6.81, yeah. Anyway, so let me go back. Let me go back here. Ready here. Can you do this quiz? Okay, I'm going to skip a couple of these. So I got the equation right so far. I got 1.55. Okay, that's what I got. And then you said I got a position of 6.8, and that's what I got. Did you get it wrong?
We don't know if we got it wrong yet.
Oh, okay. So yeah, so I think you got it right. That's what I got on my first try, and I think you got it right. So unless you hear different, don't be concerned. Yeah, good job.
I know you probably already went over the first question in the quiz, but
oh no, I didn't.
Wondering, oh, you didn't?
No. That was
It's just-
actually the first. That was the first one. That was quiz question number 1. Yeah.
No, that was the second question, I think. The one you just did.
I'm sorry. What I meant by that is that's the first one I did today. Number 2.
Oh, yeah.
Yeah.
Well, the first question is really, it is really easy, I think. It's just asking for the average velocity between 2 time intervals. And
Okay.
and I first did change over distance over change over time. And then I got 0 as my average velocity, which I know is fine. But then I was concerned by that. So I derived the position equation to get my velocity equation. And then I did the same thing, but plugged in my, I did velocity at the end minus velocity of the first time, which gave me a different answer.
Yeah. Okay. Do you have the ability to share your screen so I could?
Yeah, I do.
And yeah, move it so I can see the question. The reason I say that is because there might be a little subtlety here. So an object's motion is described by this function. Calculate the average velocity between the times 0 and 2. Okay. Now, let me just, before I lose your formula here, let me put here 6t minus 1.5t. Is that t cubed there?
Yeah. Oh wait, am I muted?
See the calculate the instantaneous acceleration. Okay. So the first one, if I'm reading this right, is your average from an interval of 0 to 2. And your second one is calculate an acceleration at a half a second. Enter your answer and show your work. Oh, and you've done some work here. Yeah, let me just be a little careful here. So what did you do? It looks like you took okay. Yeah, I'm trying to. So, okay, so the one you circled first, the upper one, you took the velocity, or is that the position? See, that's where I think what, yeah, your instructor is getting at here is to take the position, and it must have changed directions because you get a change in position of 0. Yeah, and that's what, I'm sorry, it took me a little while. I think I'm catching on to what you're trying to say here is you're a little bothered by the fact that you got a 12 at both time equals to 0 and at time equal to 2, right? And that, yeah. Okay.
Let's start. Yeah. Am I unmuted?
Yeah, you're unmuted. Yeah.
Okay. Yeah. So
yeah, no,
yeah,
I think your first one is right because you just want to go, what is your the average speed is just distance divided by you know, the change in distance over the change in time. That's the average. It's not a derivative. It's not an instantaneous one.
Okay, so it wouldn't be the same. So that, okay, because I took the derivative, but then I still did the t at 2 and minus t at 0. I just plugged it into my velocity equation right here instead. But just because like I wasn't liking this answer.
Yeah.
But
yeah, I'm not sure what the one where you got the -12. I'm not real sure what you're doing. It looks like you've got a change in velocity. But you took velocity at 2 minus the velocity at 0. But change in velocity is not the way to get the average velocity, I guess is what I'm saying.
I see. Okay.
The change in,
So then this
yeah.
so then this would be right. This one.
Yeah, if I'm reading this correctly, because he says the average velocity, and the average velocity would be just the change in the distance divided by the change in time. Yeah, and that's what you did in your one that you got a 0 for the answer.
Right.
Change
All
in
right.
position. Yeah.
Thank you.
Yeah, sure. Sorry, I didn't see that right away. Oh, hey, what time did we start? I think it's break time, isn't it? It looks like Scott's back here, but why don't we take a little break and I'll be back at 3, okay?
All right.
All right.
Let's see, how do I hit stop record?